Okay, let's jump right into this new paper. It's called SimpleMem, Efficient Lifelong Memory for LLM Agents. For anyone out there building stateful, complex agents, this really looks like it could be the blueprint we've been waiting for to get past the context window problem.
It absolutely is. And for the 1-minute summary, here's the core of it. LLM agents that have to do long-term, multi-turn tasks, well, they've always been hobbled by a few key issues. You've got the context window limits, of course, but also a massive buildup of useless noise and just astronomical inference costs. We're talking up to 16,900 tokens for some of the full context models.
That is just a staggering amount of compute, especially if you're trying to scale that.
And SimpleMem just tackles this head on. It's a memory framework built around what they call semantic lossless compression. And it uses this really disciplined 3-stage pipeline: compression, consolidation, and retrieval. The results, they really redefine the efficiency frontier for these agents.
So how big of a gain are we talking? Give us the numbers.
SimpleMem doesn't just get state-of-the-art performance. It hits a 43.24 average F1 on something like GPT 4.1 mini. It also radically boosts efficiency. It cuts the inference time token consumption by up to 30 times, 30x.
Wow.
Yeah, compared to those full context models. It averages only about 530 to 580 tokens for each query. So they've basically established a much, much better trade-off between how well it performs and how much it costs to run. That's really the mission of this paper.
A 30x reduction in tokens for better accuracy, that's a complete game changer. Okay, let's start the deep dive. Let's really look at the pain points they wanted to solve. We all know LLM agents are stuck with a fixed context window, which is why they need external memory. But what were the existing solutions getting wrong?
Well, they mostly fell into 2 traps. The first failure mode is what the paper calls passive context extension. Think of systems like Locomo, or even some of the earlier versions of MemGPT. These they just retain the full raw interaction history.
So basically just appending the whole conversation to a giant text file and then feeding it back in.
Exactly. And you can guess the result. Massive redundancy. Over hundreds of turns, you just collect so much low entropy noise, social filler, okay, got it, repetitive logs, chit chat, and it just dilutes the actual signal. That huge volume of low information history is what's driving those 16,900 token queries.
And it also makes that middle context degradation problem worse, right? Where the model sort of forgets important stuff that's buried in the middle of a huge pile of useless data.
Precisely. The system is getting burdened computationally and you could say degraded cognitively just from sheer volume.
Okay, so that's the first group. And the second, the iterative reasoning approaches, they tried to fix this by actively filtering or summarizing. Why do they still fall short?
The problem there is the online filtering process itself. You have systems like AMEM or MEMZIR, and they try to cut down the noise by running repeated inference cycles, making summaries, building knowledge graphs, all during the conversation turn.
So it's a latency problem.
It's latency, and it's also still token cost. MEMZIR might use around 980 tokens, MM over 1,200, just for that filtering and reasoning layer. SimpleMem wants to get that filtering efficiency without having to do all that expensive inference work right when the query comes in.
So SimpleMem's goal, which they say is inspired by the brain's complementary learning systems theory, is all about improving the quality of the information, making sure every single token in that fixed budget is a high-value one. Let's get into stage 1, semantic structured compression. How do they filter the input right from the start?
The core idea is to stop low-utility content from ever even getting into the permanent memory index. They take the incoming dialogue and divide it into these small, manageable chunks overlapping sliding windows. They call them 12.
What kind of window size worked best?
They landed on a fixed length of 10 turns for the window, with an overlap or a stride of 5. It's a really clever way to make sure you don't accidentally chop an important conversational idea in half right at the boundary.
Makes sense.
And then comes the filter, the entropy-aware filtering mechanism. It basically computes a quantifiable information score for every single chunk.
And what goes into that score? This seems like the most important part of the filter.
It's a dual criteria thing. They look for 2 signs of significance. First is the introduction of new named entities, a sign that a new person, place, or thing has just entered the chat. And second is semantic novelty, which they calculate using cosine similarity against the history. If the new window is too similar to stuff we've already talked about, it gets a lower score.
So it's looking for both new facts and new concepts.
Exactly. And make sure the window isn't just redundant chit-chat. And if that window's information score falls below their significance threshold, which they found is about a $3,500, that segment is just discarded. Gone. No more. Got it. Thanks for the update. clogging up your memory.
That is some powerful pruning right at the front door. So the stuff that makes it through becomes a memory unit. But these units have to be usable later on their own, right? Which brings us to the normalization steps.
Correct. The goal is to create these compact, context-independent memory units. And this happens with two essential fixes. First is coreference resolution. You know how we use pronouns like he agreed or she needs it. In a long-term memory, those references become ambiguous almost instantly.
So SimpleMem just resolves those on the fly.
Yes. It replaces the ambiguous pronoun with the actual entity name. He agreed becomes Bob agreed. Now, it doesn't matter when or where that memory unit gets retrieved, its meaning is totally self-contained.
That's essential. And the second normalization step handles the timeline problem, which I know is a huge challenge for multi-session agents.
That's temporal anchoring. This might be the most powerful piece for temporal reasoning. Think about it. You talk to an agent today and say, I'll order that next Friday. The session ends. If the agent loads that raw memory unit 2 weeks from now, next Friday is either meaningless or, worse, it points to the wrong date.
Because next Friday is relative to when you're retrieving it, not when it was said.
SimpleMem converts all those relative expressions, yesterday, next week, into absolute ISO 8601 timestamps, right at the moment of ingestion. By locking in the time reference, they solve that ambiguity completely. This step alone just proves why structured data is so much better than raw text storage for memory.
Okay, so we've filtered the input, we've normalized the facts. Now we have to organize and synthesize all this, which is stage 2, structured indexing and recursive consolidation. How do they index these little atomic facts to make them easy to find?
They use what they call structured multi-view indexing. It's a system with 3 layers. They recognize that just a single embedding vector isn't really enough for the complex queries agents have to deal with.
Why 3 layers? Can't you just use one dense embedding like in standard arg?
Well, a single dense vector, the semantic layer, is great for fuzzy matching. You search for hot beverage and it pulls up the memory for latte. But it's not great if you need exact details. That's why they add a lexical layer, which uses a sparse representation like BM25. This makes sure that exact keywords like a project name or a client ID don't get lost in the vector space.
So you have conceptual search and literal search. What's the third layer?
The symbolic layer. This is just structured metadata, timestamps, entity types, topic tags. This lets you do deterministic filtering with SQL-like constraints. So it's like searching Google for concepts, Wikipedia for exact terms, and a database for filtered data all at once.
That flexibility is huge. Okay, now for the really clever part, recursive consolidation. This is the bit that's inspired by biological memory, like how our brain reorganizes things while we sleep. How does SimpleMem do that in the background?
It's an asynchronous process. It's always running, trying to prevent the memory from getting fragmented and redundant over a really long time. It scans memory units and computes an affinity score between them. And this score is very carefully balanced.
Balanced between what exactly?
Between pure semantic relatedness, so how similar the content is, and temporal proximity. They add a temporal decay factor to prioritize consolidating newer related events first.
Okay, so if I talk about ordering a coffee every Monday for 5 weeks, those events are related, but they're spread out over time. The system needs to find them, group them, and then synthesize them.
Precisely. When a cluster's affinity score gets high enough, those individual units are synthesized into a higher-level abstract representation. This is the key to reducing the active memory footprint. So instead of storing 30 records of the user ordered a latte, the abstract memory just becomes the user regularly drinks coffee in the morning. This high-level abstraction is absolutely critical for long-term reasoning.
So we've processed the input, cleaned it, indexed it 3 ways, and abstracted the patterns. Now we're at stage 3, Adaptive Query-Aware Retrieval. Even with this super high-density memory, why is it still a mistake to just retrieve, say, a fixed number of documents?
Because your context is finite, and your tokens are expensive. If you retrieve a fixed number, say $10 on, for a simple question like, what is Bob's last name? You're just wasting tokens on 7 or 8 useless documents. But on the other hand, if you have a complex query like, did Bob agree to the terms from last week, and what date was that? Then $10 might not be enough.
So SimpleMem needs to figure out how many memories to retrieve based on the question itself.
Exactly. They start with a hybrid scoring function that combines signals from all 3 index layers, semantic, lexical, and symbolic to rank candidates very precisely. But the real innovation is the query complexity estimation.
They use a lightweight classifier for this? Is it just looking at how long the question is?
It's a bit more sophisticated. It looks at the structure of the query, certain keywords that might indicate abstract reasoning, and crucially, the level of abstraction it thinks is needed. Is this a simple fact lookup, or does it need to pull together multiple facts from different times?
And based on that complexity score, it adjusts how many documents it retrieves.
Yep. If the score is low for a simple fact check, the system retrieves a minimum number, maybe just 3, and it prioritizes those high-level abstract memories. If the query is complex, the scope expands up to a maximum depth, maybe 20, pulling in all those fine-grained details you need for deep reasoning. This adaptive pruning is really the final piece that controls the context bandwidth and gives you that amazing accuracy with minimal waste.
The results really do speak for themselves. They used the Locomo benchmark, which is known for being really tough on temporal reasoning and tracking things over long conversations.
And the results are just overwhelming. SimpleMem got state-of-the-art performance. The average F1 score of 43.24 on GPT 4.1 Mini wasn't just a little better. It blew Mem 0, which was at 34.20, out of the water. That's a huge difference for just optimizing the memory part.
And what about that temporal reasoning score? 58.62 F1, that's massive, and it directly proves that the initial semantic structured compression, especially that temporal anchoring step, is working perfectly.
Absolutely. But let's get back to the elephant in the room. Token efficiency. Full context methods were using around 16,900 tokens. SimpleMem needs a mere 531 to 583. That is the 30x reduction we talked about, and that translates directly into huge cost savings. And even compared to other optimized systems like Mem0, SimpleMem is still used 40 to 50% fewer tokens while being more accurate.
And the efficiency isn't just tokens, it's about raw speed, right? That affects the user experience. Well, looking at these latency numbers, the memory pipeline itself is way faster.
Yeah, they have the fastest memory construction, only 92.6 seconds per sample. To put that in context, that is 14 times faster than Mem0 and over 50 times faster than AMEM. And that speed up comes directly from that single pass compression. No more time-consuming iterative graph updates.
So faster processing, cheaper operations, higher accuracy. Plus, they showed that this kind of memory structure can really elevate smaller models, which is so important for deploying on-device or on a budget.
Yes, that was a great finding. When they paired SimpleMem with the smaller Qwen 2.53b model, the F1 score was 17.98. That same Qwen model using Mem0 only got 13.03. Just shows that the quality and density of the memory you give an agent can be more important than just the raw parameter count. High-quality context helps smaller models reason much better.
Okay, before we wrap, we have to look at the ablation study. This is where they proved that every component really matters. When they started surgically removing parts of the pipeline, what broke the most?
They used GPT 4.1 Mini for this. So first, let's look at semantic structured compression. When they took out the normalization, so no coreference or temporal anchoring, and just used standard chunking.
I'm guessing temporal reasoning just completely fell apart.
It was disaster. A devastating 56.7% drop in temporal F1. This one finding just proves that context normalization fixing pronouns, changing yesterday to a real date, it's not a luxury. It's the absolute foundation for any agent that needs to track timelines. Without it, the agent's reasoning about time is completely broken.
And what happened when they turned off the background organizer, the recursive consolidation?
Removing consolidation caused a 31.3% decrease in multi-hop reasoning F1. This shows you how important that abstraction is. If the system can't turn 30 small facts into one big pattern, it has to try and retrieve all 30 fragmented pieces to answer a question, and that just chokes the context window and the LLM fails.
And finally, what about getting rid of the smart adaptive retrieval and just going back to a fixed depth?
That led to a 26.6% drop in open domain F1. So that confirms that you really need that dynamic complexity estimation. If you retrieve too much for simple queries or not enough for complex ones, the agent's overall robustness just plummets.
This paper really does feel like a paradigm shift. SimpleMem treats memory like a dynamic, almost biological process. It filters input, it consolidates facts while it sleeps, and it adapts how much it retrieves based on what it needs right now. It's the difference between a raw hard drive and an actual learning system.
That's the perfect way to put it. But if you take one thing away from this whole deep dive, it should be the final provocative thought that came from their sensitivity analysis. They called it rapid saturation.
Ah, yes. The test where they changed the number of retrieved documents to $.
SimpleMem got to nearly 99% of its peak performance with only Keta 333 retrieved entries. It hit an F1 of 42.85 with just 3 documents, and barely improved up to 43.45, even when it retrieved the maximum of 20. This completely challenges a core assumption in RA design, which is that you succeed by just throwing a huge volume of context at the problem.
That is profound. It suggests that if you can reliably create these perfect, context-independent, abstracted memory units, the whole game changes. The key isn't about maximizing the context window or retrieval volume anymore. The key is maximizing information density. If you only need the top 3 most relevant facts to answer a complex question perfectly, it proves your memory system has done its job. You might want to think about how this density over volume idea could change how you build your own agents.